So welcome to this screencast on how to do the logic circuit questions that occurred in Logic Circuits lesson 2 for year 9. So we're going to go through those questions. I'm going to work through them now. But just a quick recap. Logic circuits are used in many different applications for control purposes. If you look at that little light by your front door that comes on at night time, hopefully, if somebody moves around near the door, that's a simple logic circuit controlling when to activate the light. And they usually incorporate some kind of sensors. In that case, there's two sensors. There's a motion sensor and there's a light dependent resistor, which can determine whether it's day or nighttime conditions. So we're going to have a look at these, but let's just remind ourselves of the basic gates. The basic gates are the NOT. So if you've got an input into a NOT gate and you've got an output B, then A can take the values counting up in decimal. A can be 0 or 1. In binary that happens to be the same, it's just 0 or 1. B in this case is going to be inverted. So A represents like a voltage, if you like. So that voltage, we know that in binary a voltage represents a 1, no voltage represents a 0. So if A is 0, the NOT gate is going to actually send a voltage out the other end, so B would be 1, because that's just its purpose, that's just what the NOT gate does. Think of the actual gate and how it works on its internals for now as just a bit of a black box. Okay. Then we've got the AND gate, which takes two inputs. So we've got an A and a B on the input now, and a C on the output, and we've got A, B, C. Now if we count up to get the values of the inputs on this side of A and B, the way to do those is a very specific order. So you count in denary, you go 1, 0, 1, 2, 3, so on. So it's 0, 0, 0, 1, 1, 0, 1, 1, and then you keep going. It's oh sorry, no, you don't keep going, that's it. So that's the four inputs we can get from two inputs. That's all the combinations, and that represents the number 0 to 3. So that keeps the order nice and consistent when you're doing logic truth tables. Okay. So in this case, this particular gate, thinking of it as a black box, what it actually does is if either input is 1, you get no output. You only get an output when both inputs are actually 1. So you can put the 1 there, and the rest of the outputs would all be 0. Many apologies, by the way, there's a huge thunderstorm running outside, and that's what you're hearing in the background, and the lightning. But carrying on, then you've got the OR gate. Okay, so we've got A and B as inputs, and the job of the OR gate is if either of those, and we do the counting again in denary. So sorry, we don't have a 4, so it's 0, 0, 0, 1, 1, 0 is 2, 1, 1 is 3. Okay, so that's our four inputs. This time we've got the output C. So C would be 0, 1, 1, 1. Okay, so those are your three basic gates. So if you look at the first question gave you this logic statement. It gave you, so number 1, it said A and not B. Now these statements, these logic statements written out there with brackets and things, there's some simple rules about precedence. Just like in mathematics, if you add 2 plus 3 times 4 in maths, I hope most of us would know the answer was 14 or not 20, because we don't do the plus first, because the highest precedence is in the multiplication. We remember that from bid maths, and brackets are included. Well, with logic circuits, the precedence is not, it's the NOT gate first as the highest, well, it's brackets first, sorry, brackets first, then it's NOT, then it's and then it's OR. Okay, so that's the order of precedence for logical operators in these circuits. So what we kind of do here, there's different ways of going about this, but we can start on the left hand side to draw the circuit, or on the right hand side. It depends on your preference, but I'll start on the left hand side. So I can see here that we've got brackets, which are the highest precedence. So I'm going to do that first, and inside those brackets we've got not B. Now any of these letters here, like A, B, they're instantly inputs. So you can almost like label those up straight away on this side of your circuit diagram. It's A and B, they're inputs. Okay, so they just represent voltages which are on or off, which represent zeros or ones. Okay, so here inside this bracket I've got not B. So I've got to put, sorry, not B, wrong place, my mistake. So I've got to put B through a NOT gate. Would you just ignore that for now? So I've got to put B through a NOT gate, okay, and that's that. That's the brackets dealt with. Okay, but before we carry on, every time you perform some kind of logical operation inside one of these circuit diagrams, to keep track of everything, we label these kind of intermediate values inside the circuit. They're not outputs because we haven't got to the final output yet, but we label them so we can keep track of them in a truth table. And usually I just carry on from where the inputs finish off. So in this case we've got A and B, so I'll call that one C. At the top here we've got A. So now we've got to do, we come out of the brackets, the next logical operator to do is this AND. So we've got A and whatever our result was from the brackets, which was actually C. So we take both of these and we put these into a AND gate, okay, and then that gives us our final output D. Okay, so we draw the table for that. We've got A and B, and the intermediate value there C, and then the final output D. So I'll just remind you that C is actually not B, and I often just write it above in brackets just to remind myself. So once again, counting up from 0, always my mistake, 1, 0, 1, 2, 3, 4, 0, 0, 0, 1, 1, 0, 1, 1. Okay, that's all the possible values. That's counting up these inputs. These inputs can only ever be that range of values, and we've put them in order of their binary equivalents, their decimal equivalents, which is 0 to 3. Okay. So now 0 and 0. Well, let's do this intermediate first. Let's do C. So C is not B. So we look at B, not B. If B is 0, not B is the inverse, the opposite of B's value would be 1, and we just fill all those in now. Now we get to our output, and to find our output now we've got to take the AND of C and A. Okay, so we've got to look at A and C and perform the AND operation, which means they've both got to be 1 for the output to be 1. So I can only see one row in the table where they're both 1, and then the rest of these times 1 and 0 is going to be 0, gives us a 0. That's how that logic works. 0 and 0 gives us 0, and 1 and 0 gives us 0. Okay, so that's number 1 completed. So moving on to number 2, I'll write down the statement. If you feel a bit more confident now and you'd like to just pause this and have a go yourself. The next one was A, so this was question 2, and this was A and B or C. So if you're feeling confident, pause now and then have a look at what I do next. Okay, so this time we've got 3 inputs, A, B and C. So we kind of, to draw the circuit, we can start off with those inputs, A, B and C. Okay, those are our 3 sort of voltage inputs into this logic circuit. We've got brackets, so let's deal with those. So the first thing we've got to do is this operator here, which is inside the brackets. To resolve the brackets, it's B or C. So we take B and C, and we put those both through an OR gate. Okay, so they both go through an OR gate. That will produce an output from that OR gate, which is not the ultimate final output of the circuit, but it's a kind of intermediate one from that little operation there from those brackets. So we'll label this D, okay, because it's just the next letter up from ABC. Finally, we've got to do this one now. We've completed the brackets part of it. The precedent says now we go to the AND. So we go to the AND, and we've got these two here to put through an AND gate to give us the final output, which in this case we'll label as E. So looking at our table this time, we've got three inputs, A, B, C. So this time we're going to have 0, 1, 2, 3, 4, 5, 6, 7. So all the 0 first, that's the same as decimal 0, and then it's 1, and then it's 2, 3, and then 4, and then 5, and then 6, and then finally all voltages on would represent 7. Okay, so now D, if you remember, D is the OR of B and C. So we're looking just at B and C now. So if either of those is on, B or C, the logic of an OR gate says that the output will be 1. Okay, so in that case they're both off. C is on, so the output would be 1. B is on, so the output would be 1. They're both on in that case, the output would be 1. They're both off, so it's a 0. C is on, so it's a 1. B is on, so it's a 1. And they're both on, so it's a 1. And then finally, to get E, so I've forgot to say I do label that usually. I usually put above B or C just to remind myself what D actually represents. And then E is the AND of D and A. So it's A and D. And I can write across the top just to remind myself. So it's A and D. So you're looking at A, column A and column D and performing the AND operation. So you're really looking for rows now where both of these are 1. So there's a 1 there and a 1 there. There's 1 there. There's 1 there. And there's 1 there. And then you know the other rows are all going to be 0 because they're not both 1. Okay. So that's question 2 done. Question 3. I'll draw out the logic again, and then you can pause the screencast if you want to have a quick look at it. Question 3 is brackets this time. A, XOR or exclusive OR, B, and C. So this time we've got a new gate to deal with, this exclusive OR, and it's the same as an OR, but the difference being that the logic of an exclusive OR is that you exclude the circumstance where both inputs are 1. So on a normal OR gate, if both inputs are 1, the output would be 1. On an exclusive OR, the output would be 0 in that case. Okay, so an exclusive OR is only activated, or the output is only 1, if either of the inputs is 1, but not both of them. Okay, so pause the video if you want to have a go at this. Okay, so we'll draw the circuit first. So this time we've got A, B and C as inputs. So I'll draw our circuit inputs there on the left hand side, A, B, C. And we've got brackets, so we'll deal with the brackets first. We've got an exclusive OR. So this time the way I remember it is an exclusive OR, and it's between A and B. As I draw the OR first, and then I just remember that it's like they sort of remind you that it's like an O, but this time you're kind of crossing it out, so it's cross for this cross here. So that's an exclusive OR gate. So you've got A and B going into that exclusive OR gate. Okay, and that'll be producing an output, and we'll call that D. That's the kind of intermediate. And then the final piece of the circuit is this AND gate between the output of this part, the AND between that and this. So C and D both go into an AND gate, and that produces our final output E. So we've got three inputs again, A, B, C. So we just count up in decimal, so it's 0, 1, 2, 3, 4, 5, 6, and then finally all on 7. And that's all the combinations of our three inputs, A, B and C. That's all the possible voltage combinations they can have. And then the intermediate D, if you remember, D is actually the exclusive OR between A and B. Okay, so we're going to look at A and B, and this time we're saying, right, 0 in that case, they're both 0, 0 in that case, they're both 0. That time B is 1, so that would be a 1. This time B is 1 again, that's a 1. A is 1, that's a 1. A is 1 again, that's a 1. This time they're both 1, and with the exclusive OR, that means its output would be 0, because it produces 0 and both voltage inputs are high. And similarly for the bottom row. So now we go to column E, which is the AND of, sorry, did that wrong. It's the AND between D and C. Okay, so we're looking at column D and column C, and we're doing an AND operation. So we're looking at two zeros there. That's another 0. This time they're both on, so that's a 1. 0 and 1 would be 0. 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 1. Okay, so that's question 3 done. Now I'm probably going to leave 1, 2, 3. I'll leave question 4, but I'll go straight to question 5 now, which is probably the most complex one out the set. But we're doing what we're doing step by step now, so we're not phased by question 5. But question 5 is just more complicated because it's got 4 inputs this time. So if you remember, for 2 inputs we had 4 rows. For 3 inputs we had 8 rows. For 4 inputs, I think we can guess how many rows we're going to have. So this time we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 11, 12, 13, 14, 15. We will have 16 rows in our truth table. But let's draw our circuit first. So the expression we're doing, the logical expression, is A or B in brackets and we've got inside this second bracket not C, and that's or D. Okay, so we've got, this is more complex because we've got more inputs and we've got this idea of nested logic here. We've got not C in brackets within brackets with an or statement. So there's quite a bit going on. But remember our rules of precedence, which was brackets first, and then it's sorry, brackets first and then not, and then then or. Okay, and it might help if you find that difficult to remember. Come up with some crazy way of remembering it, you know, like the bidmass type thing, or some little story to yourself. So in terms of drawing the circuit, let's we can start with either the set of brackets now. We can start with the left hand side or the right hand side of brackets. I'll start with the left here. We've got, did I say 4 inputs? So we've got A, B, C and D as inputs to this circuit over here. And on this side, the first bit we've got to deal with in the brackets is A or B. So we take A and B and we put them through a regular OR gate. Now we'll call that intermediate output E, because that's just the next letter that's available after A to D. So we've got an intermediate output there of E. We've dealt with the first bracket over here. So now moving over to the brackets over here. Now when brackets are nested, you deal with what's inside the lowest sort of level of bracket. So we go inside these brackets here, and we look at this expression and we say, okay, but within that expression, that OR statement there's a bracket here on the left, so we deal with that bracket, so it's not C. So we've got to take C, and we've got to invert it by putting it through a NOT gate. That will produce another intermediate output, we'll call that F. So we've dealt with that bracket, but now we've got this whole bracket to deal with. So we've got the OR statement, we've got basically what's going to be F or D. So we take the not C, which is F, and we OR it with D. Okay, so we take D and that, and we OR that. Okay, and we'll call that intermediate output G. So we've got to E and G, and the final operation is this one in the middle, this AND. So we've got to put E and G through an AND statement. Okay. So that's the table we've got to draw out up here. So we've got our inputs, which are A, B, C, and D. I find I often make mistakes at this stage, just simply counting up, putting the binary code down for these denary numbers. First one's not too tricky though. 0 is all zeros. 1 is that. 2 is that. 3 is that. 4 is that. 5 is that. 6, 7, then we've got 8, we've got 9, 10, 11, 12, sorry, 13, 14, and then finally 15. So that's all our inputs. So all those voltages, the combinations that you can get from 4 voltage inputs, are represented there now in that table. And hopefully I haven't made any mistakes. So we go to our first intermediate input, which was the result of putting A and B through an OR gate, and that was E. So if you remember, E is A or B. Okay, so you look at columns A and B and you perform the OR operation on them. Okay, so there's a 1 there, there's a 1 there, 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 1 there, 1 there, 1, 1, because it's not the exclusive OR, it's just a regular a normal OR. So this one, now looking at F, column F, if you remember you get F by doing a NOT on column C, so it's NOT column C. So you look just at column C. Sometimes good to use something to line up these columns, you know, like a pen or a piece of paper or something, just so that you don't get muddled. So we're not in C, so C is there, so it's the inverse of whatever's there. Okay, and then the final operation is where we now work out this, sorry, not the final, the penultimate one is where we've got to work out this intermediate input called G. Pardon me. And G is a combination of an OR operation on the intermediate F and D. So it's F or D. That's what G represents. So we're looking at columns F and D. Okay, so we're looking at these two columns now, F and D. And we're carrying out an OR operation. So if F is 1, D is 0, it's 1. D is 1, F is 1, it's 1. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, final one is going to be output H, which is here, which is just the AND of G and E. So it's G and E. I'm struggling to just squeeze that on my piece of paper. So we're looking at G and E, these two columns here, and we're performing an AND operation. So we're really, ANDs are, I find ANDs much easier to fill in because you just scan the rows, and I'm just looking for where they're both 1. If they're both 1, I just put a 1. There's another one there, 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 and then all the other instances that I didn't scan 2 1s are therefore 0. Okay, so that was a much more complex example, but good luck with today's sheet. Today's sheet's a little bit more complex. It's got some straightforward circuit drawing, some logic tables to draw up, but it's also got some that really make you think in terms of I've left some things missing on the sheet, and you've got to really work out what that could be, what gate that could be. But it starts simple and it gets progressively more difficult. So if you hit a level of difficulty where you're not really coping very well, don't worry. If you've completed the first 2 or 3 questions, you're doing fine.